Okay, we are recording the meeting. Everybody should have a nice message there that you can click and either leave the room if you value your privacy, or you can stay if you don't. Use Amazon or Google, you've already lost all of your privacy. They know everything about you. Okay. Well, let's go ahead and get started. I wanted to, first of all, bring your attention and kind of go over the homework and answer any questions. Plus, I did a sneaky thing on you. I went ahead and added a couple of homework problems, as we'll see. So I'm going to, I guess I better go back here and share my screen. Okay, hopefully everybody can see my screen. And there it is. Okay, so one of the questions, there's a number of interesting questions here. And I wanted to see if there's any questions that you might have on this. So let's go up here. We talked a little bit last time about the prolate and the oblate spheroid. Anybody have an answer to that as of yet? It's an interesting problem. Are you totally in the dark?
Yeah, let's see. I guess
I read the Wikipedia article, so I kind of know what the scaling looks like on that, I suppose. But
okay. So what would you do? How would you magnify it? You can magnify or demagnify in the T1 axis, T2 axis, and T3 axis, and there isn't a unique solution. I'm just looking at kind of it as a thought experiment here.
see, I don't remember which one was which, but I remember the difference was basically you choose one of the axes and you either expand on that axis or contract on that axis.
Okay, here's the way to remember it. Ready? A prolate spheroid is like a football. Football. Okay? So a prolate spheroid is like a football. So how would you do that one?
You'd expand on one of the, I guess, the x-axis, you could say, for the.
Yeah, you just expand on one of the axes. That's exactly right. One of the axes has to magnify more than the other two, which you probably keep the same. That will give you the prolate spheroidal shape. And again, prolate football, pro football. And then the oblate. What do you do with the oblate, Adam?
You contract one of the axes.
Yeah, you just shrink it. Or you can expand two of the axes and leave the other ones the same, but yeah, it's all the same. So that's all I wanted out of this. And the other thing which is interesting is I don't think most people think that there are two types of ways you can squash a sphere. And indeed there are. You get the oblate and the prolate. Let's talk about this. Have you had a chance to look at this one yet? Did the following operations commute? Has anybody worked on this as of yet? If not, you will be working on it for next Tuesday. Let's do the rotate and shift. Do rotate and shift work? By the way, what do you do to have to disprove one of these?
A counterexample?
Just show one counterexample. Just show one counterexample. And if you can show one counterexample, then there's not a commute. Another way, which is more difficult, is to come up with the general matrices for rotate, and you can do that for scale, and see if the matrices commute, right? If you think about that, because if you rotate and scale, then in one case you're multiplying by the rotation, then the scale is at the same thing as multiplying by the scale and the rotate. So the commutivity, at least intuitively, that I'm asking for here, can also be related at the matrix level, where we examine whether the matrices, the scaling matrices, commute. Did anybody get any of these? Did anybody hurt themselves trying to get any of these?
I got them.
You got them? Okay. So let's, should we ask Chris? By the way, I got to take notes here. Chris, do any of these commute?
I got that C and D commute.
Transpose and
Scale and
scale?
rotate and transpose and scale.
Transpose and shift. Okay.
No, he said transpose and scale.
Yeah. D and E, is that right, Chris?
C and D.
C and D. Okay, rotate and
trans-
scale and transpose and scale.
Transposing is flipping the axes, right?
Yes, yes. Transpose is flipping the axes. Okay, so these are all things which you're going to work out and hand in next Tuesday into box. So 39, let F sub rho be the Hankel transform of FR. What is the Hankel transform of FR is equal to 1? Did anybody get this one?
I got a delta at rho. Delta of rho.
Delta at rho.
Delta of rho.
Huh. I'm going to have to think about that one. The proper answer is delta U1 delta, or I'm sorry, delta U1 delta U2. In other words, a little spike at the origin. Because remember, when you do a Hankel transform, it's exactly the same as doing a 2D transform, right? That's the thing that we have to be used to. So you can do a Hankel transform of 1, but that's the same thing as doing a two-dimensional Fourier transform of 1. 1 is kind of a degenerate circularly symmetric function, isn't it? In a very degenerate case. Because if you rotate 1, well, it kind of stays 1, doesn't it? So therefore, it stays that way. So if we know that if we do a two-dimensional Fourier transform of a 1, we get a spike at the origin, a direct delta at the origin, del of U1 times del of U2. And the question that's going in my mind, Chris, and I don't know, maybe you thought about it, is this the same thing as delta of rho? I think it might be. I'm going to have to give that some head scratching. It isn't apparent to me right now, but it indeed might be the same. Okay, anybody get B? You better have got B because we worked it out in class. Okay, no one got B? Okay, Chris?
E to the minus pi rho squared.
Yeah, remember we said in class that this was the only place where you don't have to use a Hankel transform because r squared is equal to x squared plus y squared, right? And if you substitute x squared plus y squared in B, you get a separable function. Apply the separability theorem. Slap them back together. Okay, C, I'll ask Chris about this one too. If you scale a circularly symmetric function, what do you get? This is a little bit more tricky because we're taking a circularly symmetric function and we're scaling it.
I got 2 pi m f of mp.
2 pi, I don't believe that's right.
There's no 2 pi?
I don't believe there's a 2 pi, and I think there's an m squared. So be very careful in that. Just carefully substitute into the Hankel transform, and then do your very careful substitutions and see what pops out. And I believe that you'll get m squared times the oppositely scaled Hankel transform. Because don't forget, in C, we're scaling in 2 dimensions, aren't we? We're scaling in 2 dimensions. We're scaling in T1 and we're scaling at T2 at the same time because of the R squared, right? So we get one scaling out as an M. We get the other scaling out as an M. So that comes out as an M squared. And that should come out in the math very, very nicely. Okay, D, an annulus equal to 1 over this strip and 0 otherwise. So this is kind of what looks like a square donut, right? It's a donut, it's an annulus, 1 inside the annulus, kind of a washer, if you will. And it's 0 on the inside, 0 on the outside. How would you compute this? Go ahead, Chris.
I split it up into 2 rectangle functions.
No, two circle functions.
2 circle functions.
Yes.
So you have rectangle functions in the variable of r.
Yes, in R. Yeah.
So pi r over 2 beta minus pi r over 2 alpha.
Yep, that's it. So here, okay, that's enough of a hint. Notice that that annulus is a big circle minus a little circle, right? It's a big circle minus a little circle. So you can apply the linearity of the Fourier transform and do the big circle and then subtract off the little circle's transform. Is that okay? Here's a funny one. Derive the inverse Hankel transform. We didn't talk about the inverse Hankel transform. There's a big clue in the book, by the way. I hope in some of these you're going to the book and kind of reviewing, because I'm lecturing basically out of the book, skipping over some different parts, but basically lecturing out of the book. And there, the inverse Hankel transform is derived. And did anybody get this?
I got something, but I think I'm off by a sign.
A sign, okay.
I got the same, almost the same expression.
It is. It's exactly the same. It's exactly the same as the forward Hankel transform, which is really astonishing. But no, it isn't astonishing. Now, there's another way you could go about it. You could go to the inverse Fourier transform and do the variable substitutions, you know, with transforming the rectangular coordinates into polar coordinates, and then go through the same gyrations that we did before. But you get a couple steps into it and you realize, hey, we're doing exactly the same thing that we did with the forward 2-dimensional Fourier transform, except we're starting with the inverse 2-dimensional Fourier transform. We're doing exactly the same thing. And you'll find out that the inverse Hankel transform is exactly the same as the forward transform, except you switch the domains. Is that close to what you got, Chris? Okay, anybody else get that? Yeah, there should be no 2 pi's or anything out of whack here. It should be totally clean. Okay, what is the 2-dimensional Fourier transform? Now here we're going to mix up Hankel transforms and 2D transforms. We can do Hankel transforms, but here we have a circle of a radius alpha shifted to be centered at P and Q. So if you take a circle and you shift it, it's no longer circularly symmetric, is it? It's no longer circularly symmetric. If you take a circle centered at the origin and you shift it, it's no longer circularly symmetric. So can somebody tell me how you would approach this problem? A circle of radius alpha shifted to be centered at some other coordinates.
Let's see, maybe take the Hankel transform while it's still at the origin, and then apply the shift.
Yes, no, that's exactly right. That's exactly right. Were you waiting for me to exhale?
Yeah, I guess so.
I'm sorry. I shouldn't inhale. You know, with this COVID going around, I'm trying to inhale only when I need to. So, so I'm trying to do that. So let me say what David is kind of doing here. Can you see my screen now? Hopefully. Uh-oh, where did my special pen go? Okay, so whoa, something's very sensitive today for my screen. So we have a circle here on the T1, T2 plane. And the question is, what is the two-dimensional Fourier transform? I'm going to outline it for you without going through the details. First of all, you take the circle, and you know that that has a two-dimensional Fourier transform given by the Hankel transform of twice a jink, right? Is that right? But notice this can be written as twice a jink. We can always go back into the rectangular form of this. Right?
Oh,
And so,
shouldn't that be a S1 squared plus S?
oh, yeah, yes, it should be. Thank you. U1. So this is exactly the same. That's what we mean when we write down the jink of rho. So once we shift it, we know that we get the unshifted version times a e to the minus j2 pi. And let's say this is at P and Q. E to the minus j2 pi PU1 plus QU2. And that's your answer. So this is something you can slap into MATLAB or any place else that you want. And I think it's important to give your answers in one domain. It's not, I don't know, there's something non-aesthetic about giving an answer with mixed domains, with giving a, what do I mean by mixed domains? Both polar coordinates and rectangular coordinates. You should just do one. And when you destroy the circular symmetry of the problem, then just expressing your result as a function of U1 and U2 is probably the way to go. So does that make sense? So all of the stuff we've used in Hankel, we can still use with the other Fourier transform theories. The Hankel transform, the two-dimensional Fourier transform are not separate entities. The Hankel transform is a special case of the two-dimensional Fourier transform. And we can use the Hankel transform and then from that apply scaling and shifting and things of that sort. So for example, how would we do the Fourier transform of an oval? That's supposed to be an oval, not a very good oval, is it? This is supposed to be an ellipse. Is it a prolate or an oblate ellipse? It's both, isn't it, right? It depends on, you can either look at it as a circle squashed down or a circle stretched out. So there is no oblate and prolate in two dimensions. But how would you do the Fourier transform of this?
Do it with for a circle and then scale it in just one dimension.
Yeah, exactly. You would do it. You would do the Hankel transform to get the jink function, and then you would apply the scaling theorem in order to figure out how the jink scales in the other domain. Does that make sense? So all of these we can apply into two dimensions, and we can apply. I'm sorry, my train of thought had no caboose, so let me go back. All of these ideas of Hankel transform, we can always go back to the two-dimensional Cartesian rectangular coordinates and then still play around with it with the theorems of two-dimensional Fourier transforms. Does that make sense? Would you like me to elaborate on this? Anybody like me to elaborate on this idea of the Fourier transform of an ellipse? No one. Okay. You had your chance. So that's another example. Here's another one. The same as, okay, it's the same as the circle. Usually we're assuming that the circle is 1 inside the circle and 0 outside. But here I'm switching it up. We have a cookie cutter and we have a big slab of dough that goes on to infinity. And we take a circular cookie cutter and we cut a piece out of the dough and remove it. So we have a function that is 1 everywhere except where the little circular piece has been removed. So it's 0 inside of the circle and 0 outside. What's the Fourier two-dimensional Fourier transform? Okay, I'll give you a hint. Isn't the slab of dough with the circle out of it equal to 1 minus a circle? It's equal to 1 minus a circle, isn't it? So therefore, it would be, what's a Fourier? And because of linearity, we can do the individual components. The Fourier transform of 1, of course, is a Dirac delta spike at the origin. And then we subtract off the Fourier transform of the circle, which is a jink. Make sense? Let's do the same thing, except we're going to be a little bit different. The function is -1 inside the circle and 1/2 outside. From what I just explained, how would you do this?
Would you get a negative jink and a 1/2 area impulse?
Yeah, what you'd have to do is you'd have to figure out, this is, what is this? Is equal to, you would have to figure out the scaling for it. This is a scaled background. It's no longer goes up to 1, but it goes up to something else, right? And then you subtract off a circle, and you have to figure out how much you weight the circle, how much you weight the background. And so that gives you a weighted background, which you can easily transform, minus a weighted circle, which you can easily transform. You just have to figure out the coefficients in front of the background and the circle. Good? So yeah, you're right, Adam. Excellent. Here's a rough one. A circle of unit radius inside a square with a linear dimension of 2, and it's inside a square. So think of a square, and inside the square is a circle which touches all the sides of the squares. And what we'd like to do is to look at the case where it's 0 inside the circle, it's 0 outside of the square. You following my word picture? 0 inside the circle, 0 outside of the square, and inside the intersection is the, well, I don't know if it's the intersection, whatever's left has a value of 1. How would you do the Fourier transform of that? We started to get on a roll here as far as how you do this. Okay. So it would be roughly what form? It'd be a sink minus a jink, wouldn't it? Okay, Aiden, I think you have something on in the background. Or is that me?
My mic is muted.
I didn't see your mic muted.
Yeah, I have a different mic button though.
A different mic button? Okay, somebody, there was bleeding through, so I don't know. Never mind. It
I should
wasn't
just
that
be
bad.
using.
Okay, and then let's see, f of r. Now I did something here I asked you not to do. I mixed modes. I have a dt1, the derivative in the t1 direction of a circularly symmetric function. How would you Fourier transform that? Well, you go to the derivative theorem, don't you? Right? So you would Fourier transform, or the Hankel transform of f of r, then just multiply it by j2 pi u1, because that's the derivative theorem. Then let's look at 42. What is this integral in terms of the Hankel transform? It's not of, but the Hankel transform f of rho. Do you remember we had the integral theorem in one-dimensional Fourier analysis, two-dimensional Fourier analysis also, that if you wanted the area of a function, you just had to look at its transform at the origin, right? That's roughly what we're doing here. We're looking at the transform at the origin. And I'm asking you, does this extend to the idea of a circularly symmetric function? Does that make sense? No? Okay, let's try this. What's the Hankel transform? It's f of rho whoops. I'm putting it on two lines because on my screen, all of you guys are blocking where I would be writing. Okay, is that okay? So what is f at 0? That's f at 0, right? That's the Hankel transform at the origin. Does that make sense? Does anybody know what this is at the origin? That's for you to find out. And if it's 1, we just get the area of the signal, don't we? So hopefully that will help you here. I wanted to give you something on two-dimensional convolution. So I'm asking you, what's the convolution of a square with itself? And then once you're done, I'd like you to sketch it. This is an interesting problem which you won't get wrong. And then using this definition of the rectangle, what happens if you rotate it 45 degrees? Does rotation and convolution commute in some sense? We'll evaluate also this integral. And this integral is, anybody know what this is? Can anybody do this in their heads? Isn't this the Fourier transform of the Jink evaluated at u1 and u2 is equal to 0? The answer is yes. Okay. Nobody's asked me about this. What about this? Do you think this is true?
Yeah, I think a week ago I looked that up online and found they can't.
You're so serious, David. Okay. Okay, no, that's fine. Yeah, they can't. Otherwise, I guess rat poison wouldn't work, at least the article that I read. So,
Yeah, I found there's actually several different animals that can't vomit, surprisingly.
oh, what are some of the other animals that can't?
Oh, I don't have it pulled up still.
No,
but
that's okay. If you don't
some
remember,
other
that's okay.
rodents and some just other random animals.
Okay, I bet you kangaroos can't either. Aren't they related to the rat? I don't know either. Okay, can gorillas swim? Anybody look this up?
I didn't look that up, but I am wondering about that. If they can, why can't they?
Oh, that's supposed to be a stupid question. If so, why not? Yeah, I understand. That's supposed to be funny. Well, okay, you have to look this up. And can a giraffe clean its ears with its tongue? That's I find out all of these great trivia places in a place I'll tell you sometime offline. So anyway, I'd like you to do these, and then next Tuesday we will do our random selection, and then we can go through these one at a time. Okay. Okay. Very good. Well, let's get back to the lecture here, and we'll get rid of that, and then we'll get rid of this. Nope. That's what we got rid of. So let me actually get rid of this. No, I don't want to save. And we'll go to the lecture notes here. One of the things that we've been doing is laying a tool chest in multidimensional analysis. And in this tool chest, we're getting to the point where we can use it for some very interesting problems. And that's one of the things about engineering. I don't know if you've ever noticed, but most of undergraduate is analysis. As you become a graduate student, it's more applied to synthesis, where you take the results you learned at undergraduate and you begin to apply it to research and synthesize ideas from these tools that you've developed. So we're starting to develop these tools. So let's talk about it. One of the things that we're going to talk about today is tomography. Now, there are a number of different types of tomography, and there's MRIs and PET scans, and we're talking about here about computer tomography. And this is the classic way of doing it. I think if I remember right, the different types of tomography have won 3 Nobel Prizes, different techniques in tomography. And this is probably the most simple of them. And the idea is reconstruction of projections. So with this, let me ask you a question. If I stood in front of a bright light and I looked at my shadow on the wall and I began to rotate and you were able to see my shadow at all different angles on the wall and you could record that 2-dimensional shadow, do you think that that would be enough for you to reconstruct me in 3 dimensions?
I think you could get the outer shape of you. Yeah.
You could get the outer shape of me. Yeah, that's a good point. I don't think you get my nose holes, would you? Not that you'd want to get my nose holes, but there's just certain aspects that you wouldn't be able to get to. But you could get, as Adam says, the general shape from just the shadows. You could reconstruct the 3-dimensional image. Now, it turns out that my shadow on the wall is an example of what is referred to as a tomographic projection. The tomographic projection. Now, in tomography, it's kind of the same thing, except my shadow on the wall is not totally black and white. Where I am thicker, it's going to be darker, and if it just goes through my ear, it's going to be light. So the more that it has to go through, the more it attenuates in terms of the projection. And so that is the idea of if you will, a gray level projection as opposed to a black and white projection. And from those gray level projections, the question is in tomography, how we can have how we can reconstruct the three-dimensional image. And this is a well-studied operation. If you're into anybody that's an oncologist, for example, who deals with all the different types of X-rays and such, is familiar with this. By the way, here's something very interesting. Do you know, in technology, reduced to practice, relativity, I think, is applied in 2 places that I know of, and that'd be interesting to hear if you guys know of anything else. One is in GPS. Because of the technology of GPS, you have to do an adjustment of your GPS signal in order to get the right reading, and that adjustment is a relativistic adjustment. So that's one place where relativity is used. The other place is oncology. Because, for example, Dr. Randall Jean talks about imaging using protons. Well, if you get protons and they're zapping around you or zapping through you at near the speed of light, guess what happens to the mass of the protons? Does anybody remember from relativity?
Yeah, it increases.
Yeah, the mass of the mass of the particles increases. So the oncologists have to take care of that. Of course, I guess the third place that is kind of obvious is nuclear sort of energy. Relativity kind of allows nuclear energy and is the theory behind that. But surprisingly, there hasn't been a lot of reduction to practice of relativity outside of those 3 areas, as opposed to quantum mechanics, where we see application all over the place, right? In terms of electronics and things of that sort. So I think the impact of quantum mechanics is even greater than relativity. Okay, so here's the idea. Right here we have an object. This is the object that the laser is going through. And what we're going to do is we're going to do a projection. Now here's the idea of a projection. We're going to assume everything is linear. Now in practice, it isn't exactly linear. It's more of a cone shape. But we're going to take a slice, a vertical slice through here. Man, I'm having a rough time here. Let's see if I can do this better. There we go. Okay, that's as good as I'm going to get. So here's the point. This thing here, which is known as a Shep-Logan phantom, it's used quite a bit in simulations of computer simulations of tomography and stuff. You can think of this as a 2-dimensional image, right? This is, well, it is a 2-dimensional image, but you can think of it as a 2-dimensional function. And if you take a 2-dimensional function, you can always kind of rough it out. Like this. So that you have a 2-dimensional function here. Now, you'll notice if I take a slice of this 2-dimensional function, say this is a hill. I'm trying to draw a hill. So I have a hill here. These are the contours of the hill. If I take a slice along this t-axis, notice what happens. If I take a slice along this t-axis and I just look at the foothill, that's going to be a 2-dimensional function, right? I'm trying to just draw the foothill of this thing. Does that make sense? So I just grab the foothill and I do a slice through the 2-dimensional object. When I do that, I get a 1-dimensional function, don't I? I get a 1-dimensional function. Now the area of that 1-dimensional function is the projection. So when I perform this operation, what I'm doing is I'm taking the area or the integral of this 2-dimensional function slice, and whatever that is the number that I give here. And if I go to a different 2-dimensional slice, I'm going to get a different number, right? Because it's a different slice through the 2-dimensional function. So I get these results, and this is the so-called projection of the 1-dimensional function. And it's given by this expression. We have x of t1, t2 And what I'm doing is I'm fixing a value of T1. For example, I'm fixing a value of T1 right here. And if I fix this value of T1, that fixes this slice, right? And so if I use another value of T1, I get another slice, don't I? And so as I change T1, I change the area of the slices. And so what am I doing? I'm integrating along this two-dimensional function in the T2 direction. I'm integrating from top to bottom here. So I'm integrating along T2. So for a given T1, the area under one of these slices, we will refer to as a projection. And notice this projection is a function of T1, which is where the slice is located. We good? Okay, what can we do with this? Well, clearly one slice is not going to be enough. Well, let's just play around with the math a little bit and see what happens. And we come up with something called the central slice theorem, which is kind of a show that result. I once met a great researcher named Adolf Lohmann. And Adolf Lohmann was the father of the computer-generated hologram. He recognized that holograms could be made optically, but my goodness, you could also model the physics and you could compute the hologram on a computer and print out the hologram and take a picture of it and have a hologram of an object that doesn't exist. You simply created the object in 3 dimensions. You did the optics of doing the hologram. And he was really famous for that. And everybody thought at the time his computer-generated hologram would really take off. Unfortunately, we don't have a lot of computer-generated holograms today. Do you know the only place we have computer-generated holograms? Probably is on the back of credit cards, these little things here, okay? I don't know if you can see it. Can you see it right next to my finger, that little bird? There you go. By the way, if you ever want to look at a good hologram, like on the back of your credit card, go into a room where there's a single source of light. If you have a bunch of sources of light, it kind of fuzzies up. But if you go outside on a bright day and you look at that hologram with the sun, you'll find it's just beautiful. You actually see the 3-dimensional things happening on the hologram. So I was at a meeting in Mackinac Island in Michigan. And I was just a new PhD, and I was in awe of this guy, Adolf Lohmann, because, you know, I'd studied his stuff. I knew all the mathematics behind it. And I got a chance to sit down next to him on a park bench. Mackinac Island, by the way, if you don't know, is a place where they don't allow internal combustion engines. They only have one car or one ambulance in the whole island. So everybody else is riding horses and other things like that. So I sat down there next to him. I said, Dr. Lohmann, man, it's just an honor to meet you. He was from Germany, so he said in a very thick German accent, well, it's good to meet you too. I can't do a German accent. And so I said, I would like to know where you get your inspiration and where do these ideas come from? Now, since then, I've learned the sources of inspiration, and maybe we can talk about that one day, but I didn't know back then. So he smiled and he looked at me and he says, whenever I'm in doubt and I don't know what to do, I take a Fourier transform. That was his advice to me. Whenever you don't know what to do, you take a Fourier transform. And believe it or not, I've tried it a couple times in my career and it worked. You take a Fourier transform and you see a lot more interesting things going on than if you didn't take the Fourier transform. So that was Adolf Lohmann's advice. So we're going to do that here. We have this projection and it's a one-dimensional function. We have this projection. It's a one-dimensional function, as you can see. And what do we do with it? I don't know. Let's take a Fourier transform. So that's what we're going to do. We're going to take the Fourier transform of the projection. It turns out to be a very insightful and very interesting thing to do, as you'll see. Now, you'll notice that if we take the Fourier transform of this, we can substitute in the definition of the projection. What's the projection? Maybe I should maybe I should back off here. This is the integral of P of t, which is the integral of x of t1, t2. dt2. So do you see what I've done? I've simply substituted this into this expression, and this is the integral over t1, and this is the integral over t2. Is that okay? So I've simply substituted in that result. So the next thing I'm going to do is I'm just going to shuffle around the integral orders to do whatever I want. Okay. So I'm going to shuffle around the integration orders, and when I do that, I get this. This is what I get when I shuffle around the integration orders. So that's very interesting. That is the Fourier transform of the two-dimensional function as shown in the figure to the left. Well, let's do something. Let's look at the two-dimensional Fourier transform. This is the two-dimensional Fourier transform, right? Now, can anybody see, comparing this equation, how you can go from this equation to this equation? That's the Fourier transform of the projection. Over here is the two-dimensional Fourier transform. How can we make this look like this? Anybody see?
Yeah, you multiply the integrand
No.
by e to the j.
You set u2 to 0?
Yep. Who said that? Aiden?
Justin.
Justin. Good man, Justin. Excellent. You set u2 is equal to 0. If this thing goes to 0, what's left? What's left is the Fourier transform of the projection. So the bottom conclusion is that the Fourier transform of the projection is equal to x of u1 and 0. Isn't that cool? This is something called the central slice theorem, and I'm going to give you a geometric explanation here, right here. What this is saying is that if we look at x of, okay, no, I'm not going to do that. Okay. If we have this Shep-Logan phantom, and here is the corresponding projection of the Shep-Logan phantom, if we take the Fourier transform of the projection, that's the same as the slice of x of u along the u2 is equal to 0 axis. And the u2 is equal to 0 axis, of course, is this u1 axis, right? So that is really kind of cool. We have a two-dimensional function, and we have found out that the Fourier transform of the projection is equal to a slice of the Fourier transform. Now, the Fourier transform itself is a two-dimensional function, and what we get is we get not the two-dimensional Fourier transform, but just a slice of that two-dimensional Fourier transform. And this is the idea of the central slice theorem. Isn't that interesting? Now, what happens, do you think, if I take this Shep-Logan phantom and I rotate it? I'm trying to draw this thing rotated, okay? If we rotate it, we're going to get a different projection, aren't we? If we rotate the Shep-Logan phantom. But guess what? If you go through the same math, you get the slice of the two-dimensional Fourier transform going this way. The same angle that you rotated the Shep-Logan phantom. So therefore, I think you could see intuitively that if we knew the projections for all of the angles, we would know all of these slices and therefore know the two-dimensional Fourier transform. And if we know the two-dimensional Fourier transform, we can always invert back to the spatial domain and get the image, which is a Shep-Logan image. Now, this doesn't tell us how to do it. It just tells us that, yeah, you know, there's information enough there for all, if we knew all the projections, yep, we could get everything that we wanted in the frequency domain. And if we got everything that we wanted in the frequency domain, we could transform back into the spatial domain, the T1, T2 domain. Isn't that kind of interesting? And it was just a beautiful coincidence that that projection turned out to be the two-dimensional Fourier transform along a slice. Now, how do we do this? Suppose we had this Shep-Logan phantom here. I don't know what the Shep-Logan phantom is, but we project this way and we get some sort of projection, right? We get some sort of projection in one dimension. We do it this way and we get a projection corresponding to whatever this is. We do it this way and we get another projection. So the question is how do we take all of these projections and reconstruct the original image, right? One way to do it, and it turns out not to work, but one kind of obvious way to do it is, remember what happens if you have a one-dimensional function in 2 dimensions? You take that one-dimensional function and you smear it back. Do you recall that? So what if we took this and we took this function, we smeared it back here? And then we took this function and we smeared it back. And we took this function and we smeared it back. Do you get the idea? And we added all those smeared back functions together. This is the process referred to, as you see here, as back projection. And back projection sounds like a good idea, but it doesn't work. It doesn't work. And here's an example off the web of why it didn't work. Suppose, for example, we were doing tomography of a circle. If we were doing tomography of a circle, after just 3 back projections, we would get the smear here, we get the smear here, and we get the smear here, right? And notice these smears kind of leave a track in its wake, and we don't want that track. We want it to be 0 out here. I said sphere, I meant circle. We don't want this track out here. Because we just want a circle here, we want 0 outside of the circle, correct? However, if you do this enough times, if you do this 1,000 times, every one of the back smears converges on this section. All of the back smears converge on this section, and you get a really building up level depending on how many back smears that you do, back projections that you do. And your signal to noise ratio, if you will, gets better and better, right? Because that 0 in the middle gets higher and higher and higher. And compared to the smears that occur on the outside, like here and here, the smears on the outside are kind of buried because they're more spread out. So what you do is if you do many of the results, you get this. But you notice this is not a circle. This was a projection made of a circle. And you don't get the circle back. So even to the limit, back projection doesn't work. If you just do a finite number of back projections, you get these artifacts of the smear. And if you do a bunch of them, yeah, you know, the signal to noise ratio, the signal where it intersects here is really high compared to the background, but you still don't get a circle. You get kind of something that looks like a smeared out circle. So therefore, we have to do a better job. We have to do something which is better than the simple back projection. So that's what we're going to look at now. What happens when we do this? Well, there's 2 ways to do projections. Number 1 is to take the object and to have have a projection this way. I'm sorry. Okay. there's two ways to do the object. One is to do a projection this way, do a projection this way, do a projection this way, and have the object stay still. So do a projection this way, do a projection this way, do a projection this way, and have the object stay still. Or equivalently, and I think you would all agree, we could have the projection always going in one direction and rotate the object, right? It's the same result. We could either keep the object the same and rotate the projections at different angles, or we can keep the projection the same and rotate the object. The result's going to be exactly the same. It's a different way to think about it. And if you were doing it in practice, if you went in and took a CT scan, yeah, it makes a difference whether they're going to rotate the projections or they're going to rotate you. Which one do they do, by the way, if you go into the hospital and they do a CT scan?
Yeah, rotate the projector.
Yeah, they rotate the projections, don't they? But, you know, if you really want a cheap CT scanner, you would just have one scanner and you would rotate the patient, right? Like on a carnival ride. So you can see that the difference here. But this perspective allows us to look at the results here. This is the object rotated by an angle of theta. Do you remember the rotation matrix that we talked about? And so for different values of rotation, we're going to have different projections. These projections are just going to be a function of T1. So here we're rotating the Shep-Logan phantom. You can see here, we're rotating it by an angle of theta. And every time you change theta, you're going to change the projection. So you're going to get a family of curves down here that are a function of theta. Is that okay? You're going to get a family of curves that are a function of theta. And this is what this is called. This is P sub theta of T1. You're going to get different projections depending on what theta is. This is a process known as a Radon Transform. And this takes you from the two-dimensional image into the projection space. Takes you from the two-dimensional image into the projection space. But this is not what we want, is it? What we'd like to do is we would like to look at this projection and these projections, and we would like to get back x of t, right? Now notice, interestingly, that both the original image, that's a two-dimensional function, isn't it, right? This is also a two-dimensional function because it's a function of theta and T1. It's a function of two variables. So this is the reason that we call it a transform. It transforms a function in 2 dimensions into another function in 2 dimensions, the projection space, if you will. And here is what the projection space looks like. This is the Shep-Logan phantom, and this is a this is the projection space. These are known as sinograms. Oh, that'd be a great. This will be a great problem if you just do the image of a single point. You do the projections of a single point. It turns out to sweep out a sinusoid. And so that's the reason that they're called sinograms. But you can see here, theta goes this way. And T1 goes this way. So can you tell me what the perspective was? Can you tell something what the perspective is at these points? Notice right here when it's most skinny, this is the projection going this way. Why? Because at this point, the Shep-Logan phantom is as skinny as it can be, and its projection is only going to be on the cross section of the ellipse, right? Let me do it another way. If we have the Shep-Logan phantom here and we do a projection, the projection is going to be small, isn't it? Because outside the Shep-Logan phantom is equal to 0, so the projection is always going to be 0. When is it going to be fattest? What does this slice correspond to? This slice corresponds to a 90-degree rotation, because at this point, the Shep-Logan phantom is the fattest, and therefore its projection is going to be the widest. And if we just have the small aspect of it, you know, kind of the ellipse going this way is shown, we're going to get something that is a lot shorter. So I think you can see that this slice here corresponds to theta is equal to 0. And the slice here corresponds to theta is equal to 90 degrees when the Shep-Logan phantom is at its fattest. Does that make sense? You can see a little bit of the structure going on here. You'll notice something else. There's a symmetry here. And the symmetry we'll take advantage of when we do the inverse Radon transform. The symmetry is as follows. If you have an object, I hope I'm big enough for you to see me. If you have an object and you take a projection this way, is that going to be the same as the object if you, let me do it this way. If you have an object here and you take a projection this way, is that going to be the same as taking a projection this way? Is the shadow going to be the same? Taking a projection this way, is that going to be the same as a projection taking this way? Yes, absolutely. It's just that the light goes, or the X-rays go through a different side, but the shadows that they give in the projection are going to be exactly the same, aren't they? Right? So you can see this is manifest here, because if we take this big waist right here, we can fold the top part onto the bottom part, because the bottom part is just equal to the top part rotated by 180 degrees. And you'll notice it's continuous too, that we could, theta is an angle. So therefore, this is going to be periodic, right? If you do a projection at one point, if you do that projection at 360 degrees more, you're taking the same projection. So the top of this sinogram flushes with the bottom of the sinogram, and you can see it's kind of a modulus overlapping sort of thing. So if we did this for angles like for theta is equal to 0 to 1,000,000 degrees, we would just get this thing replicated a lot. But within a single 360-degree rotation of projections, this is what we get. And even with the 360 degrees, we see that there's a redundancy at 180 degrees. Is good? Is good. So here's what we get. Do you remember what happens when we rotate an image, what we do to its Fourier transform? We rotate it too. Remember that? If you rotate an image, you rotate its Fourier transform. So rotating the Fourier transform gives us these slices at different angles depending on what the angle of the phantom is. So here we are rotating the phantom. We're keeping the projection always coming from the top. And as we said, that's okay. And we go to polar coordinates here. And you notice that row 1, let's see, if we have a value of U1, and we go out here with a value of theta, isn't the T1 axis equal to U1 times the cosine of theta? We see something similar happening for the U2 axis. The U2 axis is equal to, whoop, this should be a U sub 2 here. It should be U sub 2 times the sine of theta. So we're going into polar coordinates. So this is the picture that we keep in mind as we're kind of wading through the mathematics. And again, our idea is to take this Radon transform, and this takes us the original image to its projection We want to get the projection back to the original image. That's the inverse radon transform. Okay, I think probably we'll start here because we're going to start hitting a kind of a wall of mathematics. Are there any questions about this? When there's no questions, the speaker has either been incredibly clear or incredibly opaque. I hope in this case it's the former. Okay, hearing no questions, let's go ahead and let's reconvene on Tuesday. And on Tuesday, we'll be choosing people at random to work the homework problems that I've assigned. So with that, be of good cheer, have a great weekend, and remember to inhale only when necessary, okay?
All right.
Bye-bye.
Bye.
Bye.